So for today, Maurice, the closed captioning, how are we going to do that with a AI program? Or?
Yes, you can. You have to turn it on the bottom of the screen, and then you can see it happening.
I don't need it for myself. I was just, but we want it to be seen on the YouTube. But that may be.
I don't know what that was.
I think that might be generated in real time when people watch it, actually. It's quite impressive how good some of these are. There was a time when I relied on them, but you know, I don't need them anymore. I'm lucky. But yeah, it does say that closed captioning is available, so anybody that does click on it will be able to get it. So Steve, we'll wait until about 3 minutes past before starting so that we have a few more people joining.
Sure.
Okay, for people just joining, we're waiting another minute, and then we'll start.
Okay, good morning, everybody. My name's Ian Shipsey. I'm going to chair this session. It's the third day of the MultiHEP workshop 2020, the inaugural workshop in what might prove to be a series based on the positive feedback we've received so far. So I'd like to start by saying that the positive feedback is in fact so positive that we should recognize how this workshop came into being. And it came into being because of an idea of Maurice. Maurice was the guy that thought of this, and we've worked with him to make it a reality. So I want to call out Maurice and thank him very much for the great original idea. So today's session is devoted to working with industry. And we have some really marvelous speakers to talk about the research that they do and how industry has been such a central part of that work and of what it's achieved. And so the first speaker, and we'll have 3 before a short leg break, and then 2 after the leg break, followed by a longer break of 30 minutes before moving to the panel session. So the first speaker is Steve Holland from Lawrence Berkeley National Laboratory, and his talk is entitled Working with Industry, the LBNL Fully Depleted CCD Development. So Steve, over to you.
Thanks. And, good morning, at least in California. So this talk is going to be specifically on work with industry on detector development, scientific charge coupled devices. As I'll describe later, these were first developed at Lawrence Berkeley National Lab as part of DOE detector R&D programs over the years. And then in order to make this useful for DOE experiments, we transfer the technology to industry. So I mostly want to talk about the process, not too much on the technical details, but the process of what we did and what things that worked, what things that didn't work. So just as some background, we have over 20 years of experience now working with Teledyne DALSA Semiconductor, developing these scientific CCDs. This has been of great benefit to the DOE, high energy physics, and also basic energy sciences programs. So the DOE Stage 3 cosmology projects, dark energy camera and DESI, both are using these devices. More recently, on the direct dark matter detection front with Fermilab, developed single electron detecting CCDs. There's also work in the quantum information sciences effort with that. And on the basic energy sciences part, a group led by Peter Dennis has been developing direct X-ray detecting CCDs, direct detection of soft X-rays. So this is just kind of an overview in one slide of the DOE high energy physics work with these CCDs. So hope you can see my cursor. This is the dark energy camera. Each one of these rectangles is more or less one of these 8 megapixel CCDs. This is a 150 millimeter wafer fabricated at DALSA Semiconductor. This image is taken with DCAM. This is a 16 megapixel CCD for the DESI project. These are back illuminated CCDs, so you're looking at the back of these imagers. And then this is some work with Fermilab on single electron detection CCDs with the so-called skipper CCD. And then in the basic energy sciences, as I mentioned, a group led by Peter Dennis has been developing high-speed, fully depleted CCDs, excuse me, for the direct detection of X-rays. And this is one example, tachotomography example. So that's kind of the fruits of the work. We'll go back and then talk about how this all happened, and I hope it would be beneficial for people doing other kinds of technology transfers. So this was our first publication of this fully depleted CCD in 1996. It's been a while ago. And Michael Levy was leading the group a little bit later than this, and he was strongly encouraging the commercial production of these devices so that we could produce them in the kind of volume that would be needed for experiments. So we actually produced this device in our own facility. This is a very small 40,000 pixel CCD. I have links to the technical papers for people who are interested in the technical details. But again, I'm trying to talk more about the process here. So in terms of the commercial development, we talked to the expert in the field at that time and still very active, Jim Janicek. He was at NASA JPL at that time. He was very helpful in our CCD development. So he provided us example layouts, example process flows, and he encouraged our participation in his short course back in the early 90s. For those of us who work in the scientific CCD world, this book is our reference. This is Jim in 1975. He was instrumental in taking the CCDs that he was developing for NASA projects onto ground-based facilities so that the ground-based people could see the utility of CCDs for imaging. And then recently, Jim received an Exceptional Lifetime Achievement Award from the International Image Sensors Society. And he's won numerous NASA awards as well. So he was a tremendous person to work with because for a number of things, he's very, very helpful, very generous with his time. But he had also basically scoured the field to look for every commercial company that was willing to produce CCDs for NASA space missions. And this is quite an interesting paper. I have a link to it. It talks about history, which is, kind of like the subject of what we're talking about today. It talks about some of the challenges that he faced developing CCDs for NASA. There are a number of companies. This was a 1992 paper. Most of these companies aren't in the field anymore, but Jim certainly knew the field extremely well. Now, we did not have, you may be surprised to hear, we did not have a budget like a NASA scale budget. So we were relying heavily on Jim's input in the sort of 1998 on who we might work with to transfer this technology. So looking through the old emails, there were about 4 choices or maybe less, but only one was a foundry, and that was Mitel. Now, I don't want to confuse things. I'm only talking about one company during this talk, but they went through many iterations. They were Mitel Semiconductor originally. Then they were for a short time, they were called Zarlink Semiconductor. Then their main customer bought the foundry, Dalsa Semiconductor, and then Teledyne bought them. But I may say Mitel at times, I may say Dalsa, but it's the same company. It's from our point of view. Not the same company, but the same foundry. Okay, so the foundry turned out to be very advantageous. At that time, Mitel, I think, was mostly a telecommunications company, but they were also doing CCDs. They had a pretty good volume compared to some of the more boutique CCD companies at the time. So they had a production-proven technology. They had standard process steps in place. A lot of the effort would amount to integrating these standard process steps, but we were introducing high resistivity float zone silicon that was not a standard material for processing in a CMOS type facility. So I'll talk about how we address those issues. But again, when I say Mitel or Teledyne, I'm talking about the same company. This is just email correspondence from the time. So again, Michael Levy gets all the credit for pushing the commercial work. So this was a specific email that you can read later if you like, regarding Mitel at the time. And this is Jim Janicek's introduction to us of the people at Mitel Dalsa. And Robert Grew and Raymond Frost I've worked with for the entire 20-year period. Now, I do think there's something interesting here, that we were well positioned for the technology transfer in that we had demonstrated the proof of principle by fabricating these devices at Lawrence Berkeley National Lab. And in addition, we had expertise in silicon technology development. That was Nick Palaio, who retired from the lab a couple of years ago, and myself. And this was all part of an interdisciplinary approach at the LBL Physics Division during that time, which was the superconducting super collider era. So they were, in addition to the high energy physics staff, obviously, they were hiring non-high energy physics staff like myself and Nick, who were skilled in the technology development. So main people behind that were Helmut Spieler, David Nygren, the late George Trilling was the division director at that time, and Bob Kahn became the division director after George stepped down. So we were well positioned for this. This gave us some sort of instant credibility with the foundry. These are pictures from that time. This is the equipment we had at that time. The facility is still operating. This was the 100 millimeter wafer facility at that time. A lot of this equipment has been either upgraded or like that doesn't exist anymore. This was the first CCD that we produce on a 100 millimeter wafer. The CCDs are these tiny things here, and there's an astronomical image courtesy of Richard Stover. But it would take minimum 6 months for us to fabricate this kind of device in-house. So it was challenging, of course. So I had my first visit to Mitel in 1999. Say the management was very accommodating to us. They made all their experts available to us. I spent like 3 days, 2 days there with all technical discussions. It was obvious that their technical staff was and still is very highly capable. Non-disclosure agreements are important so that you can have free exchange. And of course, as users, we should be careful obviously not to reveal anything that they would consider secrets. So we shared our expertise in high resistivity silicon processing, but we trusted them to come up with the process flow for CCDs because they were a production facility and they had far more experts on that than we did. So our process flow was just used as a rough template. So we got over ourselves as experts very quickly. We focused on what we knew about processing high resistivity silicon, but we left the hard work of the CCD development to them. And I was impressed when I was there that at that time they were sponsoring a Formula race car team. So Mitel Semiconductor. It's amazing what you can Google these days. So it took a few years for various reasons, including time to design CCDs. But this was the first production lot at Mitel then on 150 millimeter wafers. This became the DCAM CCD. These were some R&D CCDs. So sort of from 1999 to 2002 was the time frame to get that rolling. But there were some issues integrating this high resistivity process and high resistivity silicon processing having to do with the scattering layer. So again, I don't want to go over the details, but more of the process. But this layer called N+ polysilicon is very important for maintaining low dark currents. It traps what we call lifetime killing impurities, which are metals. Now this looks very simple to implement this, but it's not. And this required close collaboration and the willingness on the part of Mitel DALSA to work with us to get a robust process. And this slide is just to show you that this really does work. This is a different group. So this came on later. This is a group from Italy that looked at different gettering techniques. They concluded N+ polysilicon was the best. And we knew from our previous work that if you don't do this right, this is a dark current versus reverse voltage. It's on a log scale. Things can go bad in a hurry if you don't do the gettering right. So this is a very important process. The first issue we ran into were high particle counts, not DALSA's fault, it's just inherent in that process. So Nick Palaio suggested that why don't we repolish the front sides of the wafers to remove these particles? But that did require that we would have to go to a separate vendor to do that. And so we had a lot of detailed discussions with Mitel on how we might do this. The key point being that we implemented stringent quality control measures to make sure that the wafers did not get contaminated because they would leave their production line and go back into the production line. So that worked, that process worked. And then another thing that came up, there are 2 points I want to make here. So this problem just kind of came up a few years later, and we started seeing a repeating defect. And by a repeating defect, I mean it happens on every wafer. But one of the key things here was that we had developed rapid testing. So at the wafer level, we were doing cold probe testing. And so this is basically a dark current image. And so we were able to find, and then we would superimpose, we would sort out the images and superimpose them on the layout. And we were able to then determine that this was spatially constant across many wafers, all wafers essentially. Of course, metal contamination was suspected because it's always metal. And so this is an example of our close collaboration with DALSA. So we fed this information back to them. They then analyzed their wafer handling equipment. They generated particle maps by running wafers upside down on their wafer handling equipment. And sure enough, we were able to determine which wafer handling tool was causing this metal contamination. and then that was fixed. And then there was a similar problem, another wafer handling tool. And so it took about 1.5 years to give you a time scale, but the combination of our rapid testing and our good collaboration with them, we were able to solve that problem. And then we also did work with them to improve the performance of the devices. So this is a lower noise amplifier than this one. This is a direct connection of the polysilicon gate to the substrate. They hadn't done this process in a while, so we contributed by taking cross-sectional SEMs to look at how it was working. We saw a noise improvement from, this is noise versus integration time, about a factor of 2 noise improvement at long integration times. Now that was an example of good collaboration in terms of taking advantage of some of their more advanced processing techniques. Now, another point is that they couldn't do everything that we needed. So in our applications, we required, for the astrophysics applications, we required 250 micron thick back illuminated CCDs. That's about a third thinner than normal silicon wafers at 150 millimeters diameter. So that wasn't practical. So a hybrid approach was utilized where there's sort of the process flow. So they would process a lot of 24 wafers. They would do 80% of the processing, except for some quality control devices they would completely finish. And then they would send the partially processed wafers to us, and then we used the microsystems lab again then to do the work to make them back illuminated. So the microsystems lab went from the facility where we originally developed this device to basically the facility where we did the specialized processing to make back illuminated devices. So let me just summarize my personal opinions here. So what worked well in this case was this open culture that allowed us to talk to experts like Jim Janicek. That was extremely helpful in terms of getting it right the first time. I want to reiterate that I think that our in-house specialized expertise and facilities were helpful. And we got credibility because we'd done this before. We spoke their language. And then, as I just mentioned, the microsystem lab was key to then making the astrophysics CCDs. It also was just an outstanding industrial partner. I'm talking a little bit in past tense. I'll explain that in a minute. But I think another important thing was this was a true collaboration. We weren't just sending, filling out purchase orders and holding their feet to the fire to do that. We realized that we were not a big part of their profit loss margin, probably more on the loss margin. So we were eager to help whenever these inevitable process problems would crop up. And they're, over 20 years, you can expect that happened more than once. But we had built up this collaboration, and we were always willing to jump in when there was a problem and do what we could to help. What isn't working so well lately, government procurement rules are really complicating working with industry. This is real. I'm not making this up. I suffered immensely. Don't feel sorry for me, but we had a major issue when basically DALSA actually read the contracts and saw things like these federal acquisition rules, which they didn't feel like they needed to police their contractors in terms of these acquisition rules. And I also spoke not too long ago with a person from a major semiconductor equipment company, and the first thing that person said was, do the FARs apply? Which was really stunning because that's the euphemism for the federal acquisition rules. And he said, well, if the FARs apply, we will not bid. So this has been a problem. There have been solutions that have been implemented, but they tend to be time consuming and case-by-case efforts. So I don't know that there's a solution to this, but I do want to point out that this is a working with industry talk, and it's getting harder to work with industry for reasons like this. Okay, so I don't want to end on that down note. So I want to point out that Teledyne DALSA has been a major contributor to the DOE cosmology and BES facilities. In addition to the work described here, about a third of the LSST or the Vera Rubin Observatory CCDs were produced at DALSA via STA and University of Arizona, ITL. I mentioned earlier, I'm sort of talking about them in the past tense, though. The foundry is going away. But there are still the demand, especially in the direct arc matter world, for these fully depleted CCDs. So we're finishing off our work with DALSA. We've submitted the last designs just recently, but the direct dark matter detection efforts are funding work at 200 millimeter foundries, and we are following the same basic template that was described in this talk. First thing I did was go talk to Jim Janicic, and he gave me some ideas, and that's where we're headed. So I think that's about it for this talk. So thanks.
Steve, that was a wonderful, wonderful account. And you really helped us understand the process of what happened and how you work with industry. I think it's been incredibly valuable and appropriate for this session. So now is an opportunity.
You're muted, Ian.
No, I'm not muted. You can't hear me? You're not muted. You're fine. So now there's a chance. There's a chance now for people to ask Steve some questions. So if people have questions, could they raise their hand? Because there's a large enough group of people that if everybody speaks at once, it'll be a little bit chaotic. So who has questions for Steve? So while we're waiting for the first person to put their hand up, let me ask you a question, Steve. So what was the real motivation for Mitel, once you found them, to actually work with you initially? Was it what eventually turned out to be the case, that they benefited enormously from the credibility and expertise of your team, and at the same time you benefited from them? But did they really think about that at the beginning?
You know, I've asked that question. It's a question I have in my mind too, because clearly they weren't going to make any big money off of us. Now, they were interested in helping science, so it may not be well known, but all the Mars rover pictures that come back are done with DALSA CCDs. So they do have that history of supporting science. When I first visited, the management told us that they like to challenge their staff with new projects. And this looked like an interesting, something new for them to do with the high resistivity silicon. So that I certainly remember. They were interested in that. There were, you talk to the salespeople, you talk to the technical people. The salespeople always ask you what's the market, and we do our best to not give any falsehoods. But so I think it was a combination of. Mostly that they felt this was an interesting technical project for their staff. Sorry,
Ian, you're muted.
Oh, sorry.
Sorry, I'm muted now. How big was the company at that time? Because the way you're describing it, it sounds like it was, the personal interests of inspired leaders that recognize the benefits to everybody, including their own team if they work with you. And sometimes in really big companies, you never get to see that anymore, right? So it must have been fairly nimble.
They're very nimble. Yeah, very nimble. Pretty small at that time. The foundry, it has grown over the years. One of the reasons they're getting out of the CCD business is the MEMS business is working out well for them. So they have expanded, but I don't think there was 1,000 people, probably less than that. Small, and I got to know all the, so many people from every aspect of the fab. I got to meet everybody, and whenever something came up, I would be steered to those people. So it was small. The group that I worked with was small and very agile and very helpful.
Yeah, that sounds like a really perfect marriage.
It was.
What we need, right? What we need in companies. Now, there's some questions coming in now. So we'll start with Juan, and then after that with Gabriela.
Yes, thanks, Steve, for
for describing the history, right? But in your story, it is very clear that the role of MSL at the Berkeley, right, your lab, was very critical to make this transition happen. So my question is, if we are doing a good job now supporting the groups like your group that generated this development many years ago, and thinking about the future, right? Do we have these R&D efforts going on that could eventually translate into major productions in the industry?
I think that's true. I think the DOE K-25 support is excellent for our group. There are all sorts of issues when you have a facility like that, because they're expensive to run and they're expensive to maintain, and that's a challenge. But the detector R&D part, I think that's we're doing really well in that area.
But I can tell you it is a battle every year to maintain that level of support.
Yes, yes, I get that. I hear that every year too. So, sure.
And
our job is to try to come up with stuff that makes us worthwhile. And, we know the challenge. So,
Gabriella?
Yeah, sure. Steve, I wonder if you do see in this very successful experience something that is more a model, or it was just a specific case, unique circumstances which worked well?
I think it's a bit of both. I think you might argue that something of this complexity, it's very helpful that you could do the proof of principle. So I think that was very helpful. There certainly were unique circumstances. Yeah, I'm not really sure if I can give you a good answer on that. I would say a little bit of both, but I know that's not a great answer. Sorry.
It's okay. Probably we can also expand during the panel a bit more. Thanks.
Sure.
I'm wondering what you were saying about how it was the involvement in the SSC that led to a significant number of technical scientists being hired by the lab to enable them to play a big role in the development of the semiconductor as an approach that became so central to particle physics. But once you have that expertise, you're well then positioned to go to foundries, go to companies. And I know from limited experience I have with the CCD world is that there's a lot of experts and a lot of special tricks and knowledge that you have, and they don't like to work with people that haven't got real credibility and real knowledge as well. Right. And so would it be fair to say that if there hadn't been an SSC at the time, or if there hadn't been that interest in semiconductors, that there wouldn't have been the team at Berkeley that could have taken this opportunity and led to what happened today? And is that a fair assessment?
I definitely agree with that. I think they're really forward thinking at the lab at the time. Helmut Spieler and David Nygren, the people I mentioned before. To be really honest with you, I was reading IEEE Spectrum when I was down the hill at graduate school, and I saw an ad for a semiconductor device engineer at Lawrence Berkeley Lab, which I don't think they'd ever had that kind of need before. So I think that was really key. I think the whole SSC thing, even though it was ultimately didn't go through, but I read the book, and there was actually great funding for detector R&D at that time. But my understanding was the core program maintained their funding as well, so we had extra funding at that time. And it's just a challenge to redirect, but we had people at the lab who really saw an opportunity to take advantage of this expertise. Notably, Saul Perlmutter's group. So our group was originally led by Saul, our CCD development group. So I think the SSC was really a great thing for that. I agree completely with that.
Thank you. And thank you again for a really wonderful talk. Thanks a lot, Steve.
Thank
Now we're going to get another wonderful talk. This will be from Toki Suzuki, who's going to be telling us about Fab for the cosmic microwave background.
Mm-hmm. Can you hear me okay?
We can hear you.
All right. And I hope you can see
and
the
now
screen.
We can see your slides too, so that's perfect.
Perfect. Okay. Yeah, first of all, yeah, thank you very much for inviting me for this session. Right, so I work closely with Steve. As you can see, I'm also from LBL. And kind of how it happened is that back in 2015, I was a postdoc at the LBL. And then we thought, okay, well, cosmic microwave background is getting bigger, and then we're going to do this big next stage for cosmic microwave background experiment in the future. So let's figure out how to make a detector. And actually, people that's working on the CCD at the LBL suggested to me, hey, we had this great success working with industry to make a CCD devices. So why don't you look into making superconducting detectors also with commercial partners? And that's how it all started. Then postdoc me started looking around, and then found a few companies to work with, and then I worked with them. And now I'm a staff scientist at the LBL. Right. So with that intro, I'll be talking about how I worked with the industry to make a superconducting detectors for cosmic microwave background experiment. Okay. So a bit of a background science. So cosmic microwave background is this light that decoupled from the universe when the universe are cooled enough for the protons and electrons to combine to form a neutral hydrogen, and the photon that was coupled in the hot plasma before that decoupled and then traveled throughout the universe for 13.7, but now it's 8 billion years, and then we're detecting that we can still detect that today to learn about the early universe. There has been decades of effort. Success has been great. That now this temperature anisotropy is characterized to a cosmic variance limit for the angular scale that's bigger than about 0.1 degrees on the sky. And with that, we are able to put sub-percent constraints on the cosmological parameters. There's one parameter left called optical depth to ionization. So we are really in the era of a precision cosmology with the cosmic microwave background. So we are not done with cosmic microwave background. There's a lot of information still in the polarization state of the, start my video. Oh, hi. Okay, there's a lot of information still left in polarization of the cosmic microwave background, and by studying polarization state of the cosmic microwave background radiation carefully, we can learn a lot about whether the events such as inflation happened. We can study whether light relics, things like axions, gravitinos, these hypothetical light relics existed in the early universe or not. And we can also do a cross-correlation study with optical surveys such as DAISY and LSST to learn about dark matter and mass of a neutrino and many other science. So we are already out there taking data. So here are a list of current experiments, and there's 2 sites in the world that's really good to do cosmic microwave background science, mainly because of the weather. So Atacama, Chile, extremely dry and dry sky, so you can see beautiful blue sky, and Antarctica, South Pole, and then this balloon flight around around Antarctica is also a nice place to do the science. So these experiments what we call them stage 3 cosmic microwave background experiments, and they're on a sky with about 10,000 detectors per telescope. So now I want to talk about how detector count grew over time. So late 2000s, experiments such as APEX-SZ, SPT-SZ, and deployed with about 300 to 1,000 detectors. Then early 2010s, stage 2 CMB polarization experiment deployed with about 1,000 detectors per telescope. And then now we're in the era of a stage 3 experiment, where each telescope have about 10,000 detectors per telescope. So it's the detector count is growing over time. And the detector of choice for cosmic microwave background is transition edge sensor bolometer because it achieves photon noise limited performance. But once detector is quiet enough, we can no longer improve sensitivity by improving detector itself, and kind of way out is to increase the number of detectors, or more technically correctly, optical throughput, to improve the sensitivity. That is why detector count is growing as we want to do more precise measurement. So what's coming in the future? Shown upper right is the roadmap, or how CMB experiment is growing over time. So stage 2 had about 1,000 detectors per telescope. Stage 3 grown to 10,000 detectors per telescope. And we're proposing, okay, stage 4, let's do it with 500,000 detectors throughout the entire experiment. So there is an experiment called Simon's Observatory that we're deploying at Atacama, Chile, fairly soon, actually, with 80,000 detectors. So this is very exciting. Some people call it stage 3.5 because it's somewhere in between where we are right now and stage 4 CMB experiment. So the focus of this talk is really to solve the detector fabrication production challenge for experiment called CMBS4. So this is a stage 4 CMB experiment that will deploy telescopes in both South Pole and Atacama, Chile, with 500,000 detectors. I also want to mention there are satellite missions called Lightbird and Pico, aiming to characterize cosmic microwave background with the high accuracy, but these don't really have a high detector count. Right, so the challenge for next generation CMB experiment is, as we lower the statistical noise, of course, the understanding systematics error will become important. But when you get to a challenge of making 500,000 detectors, this production throughput really becomes an important challenge. Right. Okay. So I'm sorry about the slide without photos, but let me also mention again that this order of magnitude increase in wafer count from current experiment is the challenge. But luckily, I think kind of timing of things matched really well, that this excitement in quantum computing really expanded superconducting microfabrication capability in industry. And also there's a good match between cosmic microwave background instrumentation and this quantum computing devices, because we're both at the high frequency. Cosmic microwave background is interested in 30 to 300 gigahertz, and the quantum computing is somewhere around the 1 to 10 gigahertz. Sure, they're a little bit off, but a lot of fabrication challenges, superconducting fabrication challenges are synergetic, that we can learn from each other. So the question we asked ourselves is, can we merge industry's know-how on mass production and quality control and our knowledge on how to make the superconducting detector to tackle this production throughput issue? And I think it's good to talk a little bit about my experience and how it helped to make this commercialization happen. So this is me back then when I was in a graduate school. I got my degree at the UC Berkeley, and with Professor Adrian Lee. And he gave me a great project where I was tasked to design. So I ran an electromagnetic simulation, I did a layout, and I thought through how to make these detectors, so fabrication steps. Then I went to clean room myself and made them. So, used all the tools available at the UC Berkeley clean room to make them. So that's where I got training in working with these machines. Then lastly, I tested them in a cryogenic environment in the lab. And then I repeated this cycle many tens of times until I was able to make a working superconducting detectors for a CMB experiment. But then when I became a postdoc, because the experiment grew and grew and grew over time, I continued to work on CMB detectors. So I continued making a design, but the fabrication, we had these fabrication experts, Dr. Ben Westbrook and Dr. Chris Rom at UC Berkeley making these detectors. So it made me, how should I say? I have to learn how to communicate my design to someone else and successfully make a device. So that was really nice training that I was able to receive before tackling this commercialization, and I think that might help. So I really like working with commercial partners. And that these are just some samples of the project that I've been doing with our commercial partners. So first, detectors. We also made squid amplifiers. This is a superconducting amplifier used to read out transition edge sensors. We also made a monolithic silicon micro lens array, and then these lens array needs to be anti-reflection coated. So I worked with a commercial partner to put glass coating as anti-reflection coating on these lenses. They worked well. But I'm going to focus on the superconducting devices today. So first, there was a very strong support on this knowledge technology transfer from academia to industry from DOE. And for example, the early career research program or research award, LDRD, SBIR, and now a CMBS4 project all support this knowledge technology transfer from academia to industry to make this commercial fabrication happen. I think we're gonna hear talk later more on SBIR. And so for the SBIR, there are two phases. Phase one is smaller budget and a shorter time, and a phase two is much bigger budget and 2 years. So how I worked with commercial partners through SBIR is for the phase one, we use, during the phase one, we do proof of concept. Does commercial company have a capability to make something that's close to what we want in the end? They may not have everything, so sometimes we co-fabricate. So they do 90% of the process and we do 10%. But then if we really want to commercialize, if we keep doing that 10%, that's not really commercializing the product. So during if we successfully go to phase two, sometimes company, for example, how you read this is a seek, buy equipment that necessary to do this last 10% at their facility, so that we can fully commercialize this fabrication work at their facility. So right, so when I started this commercialization of a superconducting detector, we went out to search about maybe 5 or 7 superconducting foundry, and 2 companies were small enough to talk to us, but also large enough that they thought that they can tackle something that we're asking. And the 2 companies were SEEK and the Starcry Electronics. And they're both working on this quantum computing device fabrication. So they already knew a lot about superconducting and microfabrication steps. So my experience with SEEK. So I've been working with them since 2015, but December 2015, so it's almost 2016, a long time. So they have a PhD engineers at their company, and that speaks common superconducting fabrication language. So I start using very jargon-y phrases to describe fabrication steps or the potential issues that they may run into, and they knew right away that what I'm talking about. So that was really easy to communicate what I'm doing to them. And with their degree and many years of experience, they many times came up with excellent solutions. So it wasn't just one way. It was a very synergetic development. But it was very important to exchange detailed documentation, a specification sheet, more than when I worked with a local team at the UC Berkeley. They do have a very controlled environment compared to an academic fab where many R&D is going on. So that was nice. The process was very stable. And then they have industrial equipment that allow us to achieve high throughput that we were looking for. This is also kind of a luck. Many materials and the steps were very similar to what we do or what they do. They're using the same wafer size, very similar material. So it was easy to transfer technologies. And as the years passed, they got more involved and more interested in the technology. So they also invested a lot of fund in purchasing equipment, not 100% for the CMB detector fabrication, but that really tremendously helped CMBS for detector fabrication. So our R&D approach is to try out many different designs on one wafer So one fabrication run, we can test many detectors, many different designs quickly. So you can see this is a 6-inch wafer, and zooming in, you can see there's tens, if not 50 different designs on this single chip, and there's even more on the chip next to it. So we tested many different designs on just a single wafer to converge on a design quickly. And then once we know which design we like, we made a detector array using that design. So did it work? So here's an archive link if you're interested in reading about it. Long story short, it did. But this is kind of because the company really allowed us to have a very stable process. So for the transition edge sensor, it's really important to have a superconducting film that works for us. And what I mean by that is that the transition temperature have to be right, impedance have to be right. So it's really important, very stable process. And what they did is they gave us a dedicated sputtering chamber. They dedicated a machine for our process, which was very nice for them to do and allow us to have a very successful process. And then their superconducting film, niobium, met our requirements. So we were able to also fabricate and demonstrate that this RF circuit worked as designed, and we were able to detect linear polarization in this high frequency range successfully. And what you're seeing here is a superconducting transition. This is the current and the bias, current and voltage bias chart through the transition edge sensor. You expect to see this Nike sign, which we did. And then this is the a response of the detector to the rotating wire grid. So you expect to see this sinusoidal response. Right. So that the whole goal of working within industry is to demonstrate a high throughput. So so we decided, okay, well now we have a set process. Let's try to make a lot of wafers in one go. So we fabricated 10 wafers quickly, and then they were able to do that in 15 working days or 3 weeks. So that was our throughput goal. So we achieved the high throughput that we were looking for. But we also learned that there was some bottleneck during the process. With SBIR phase 2, actually we upgraded some of the equipment to solve this bottleneck that we identified. So hopefully we're aiming, instead of 15 working days, we can make this in 12 working days, so it'll get even faster. And with that increasing throughput, actually the cost comes down, because a lot of cost is person time and facility time, so that with the higher throughput, we're aiming to reduce the cost per detector quite a lot. SEEK also have this automated probing ability. So after we finish making a detector, they have this automated probe station that can scan through the detector really quickly and then tell us what's the connectivity yield. So 95%, which in a CMB detector fabrication, this is high. So they can use this industrial metrology process to really give us a statistics on how these detectors are performing very quickly. And that was a nice thing about working this industrial scale company. Then we do cryogenic test. And so initially we started doing cryogenic tests at LBL. We have a dilution refrigerator here. And this is a detector seeing muon hits, I think, on the detector. But then lately, this company Seek also acquired their own cryostats. They actually got 4 cryostat that can go to millikelvin. So what we're doing right now is we are working together to exchange test setup and how we do test. So they can also do a test themselves to see if detector is working as it should. And this is good because they're learning some of the not only the fabrication techniques but also testing techniques at this ultra cold temperature, and at this sub-Kelvin temperature is something new to them. So there's actually a synergy between us where they learn how the sub-Kelvin characterization works from us. And then we get the benefit that they can do some of the tests, so we can offload some of the work. So that was for the detectors. For the squid amplifier, story is a little bit different. So I also would like to mention that. So first, squid amplifier is used to read out transition edge sensors. And why we're interested in them is that at LBL, we are developing next generation of a frequency multiplexing readout technology to read out multiple TES sensors with one squid amplifier. But as we do R&D, we realized that the existing squid amplifier was not ideal, and we needed a new design. But the difference between detector fabrication and a squid fabrication is that we were not squid experts. I did not know how to design squid. All I knew was a spec that we needed. So we have a postdoc at LBL, Tucker. He calculated the spec we need. And then, luckily, we got in touch with a professor at the University of New Mexico, Professor Stephen Boyd, who knew how to design squid. And he works very closely with a company, Star Cryo, that fabricates squid. And then, so chain goes, we came up with a spec, Professor Boyd designed squid. Then at the Star Cryo, it gets made, and then that chip comes to LBL and we test them. So this is like a three-way relationship that worked really, really well. Here's a squid. It performed as we requested. So what we are looking for at the time was we wanted to lower power dissipation by order of magnitude. And we also wanted to lower input impedance by order of magnitude, and they achieved both of that. And so here's the chip they fabricated. And if you're familiar with the squid, one of the things to plot is this plot called a V5 curve, and they look great. But then using this squid, we learned, oh, there's more parameters we need to specify. So we're iterating more and more to make a better and better squid. So it's great that we now have this relationship. So we can talk to Professor Boyd, and then the chip squid gets made at the Star Cryo. So that's the end of a slide. So the summary is that the DOE provides very strong support to partner up with the industry, and that's been very helpful for R&Ds that I've been doing. And this partnership with the industry really opened up possibilities. One is to tackle production throughput challenge for SymBS4, and access to custom-made squid amplifier really allowed me to explore kind of new regime in the readout. And this relationship that I built with the superconducting foundries, it's not only useful for CMB, but for future QIS and many other high energy physics R&D. And I am talking to Seek for this superconducting microfabrication for quantum information science R&D. So no, it's great that we have this access to a superconducting fab in the industry.
So Toki, thank you very much. That was a terrific talk, and it was really on the subject we wanted to hear about today, the role of industry with scientists in our own field working together to make the impossible possible. This is terrific. We're running a little on the late side, so we're going to defer questions to you until the panel later, where we'll have ample time for discussion. So we're going to move right now to the third speaker. Thank you again, Toki. Thank you very much. We're going to move right now to the third speaker, and that's Hartmut Sadroniski. And so Hartmut, if you'd like to get ready to share your slides, Hartmut is going to talk about low gain avalanche detectors for combined temporal and spatial resolution. Okay, please start. We can see your slides, Hartmut. We can't hear your voice. You're not showing as muted, but there doesn't seem to be any sound.
How about now?
That's perfect.
Oh, okay.
Thank you. Great. Good to hear your voice. It's a voice I know well, and it's really great to hear it coming through loud.
Okay. So I want to talk about the development of low gain avalanche detectors, which are very topical now, and really talk about quickly about the needs for having detectors like this, and go a little into our results in the development, and then talk about all the other important things like collaborations, experiments, manufacturers, funding, and so on. So the needs for ultra-fast timing sensors, which means timing in the picosecond, few picosecond range, came up early, actually in 2004. One nanosecond would have been enough to help with deciding what type of next linear collider would be doing, Tesla or SLAC. Then time of flight, we looked at it with proton CT and in PET, there are some ideas how to use them. Then the high luminosity LHC came along, and there we are able to show that using these fast detectors would help eliminating background tracks. In X-phase, we have very good results. Heavy ions are starting to look at these detectors in time of flight, and for the electron-ion collider, timing and tracking is being sought. And there might actually be maps of AC LGAS coming in the future. So just to show that what I just said makes sense, there is a snow mass LOI process, which we all know, and there are actually 11 LOIs which would like to use LGAS in future experimentation, and I listed them here. I don't want to go into details naturally. But let me come now to the development of LGAS. There were really 5 phases, and they, as expected, go from the simple, the easy, to the more complicated things. What I indicated, there are a few things to take away from here. One of them is that on the right-hand side back here, where the producers are shown, it looks actually quite stable part of manufacture, set of manufacturers. The first one was the first detectors were actually built at CNM in Spain, and Giulio Pellegrini is, I believe, still logged in. He could later tell us how he had this idea. But we very quickly were able to show time resolution of about 15 picosecond for 3 layers, so about 25 picosecond per layer. I think basically the basis for this technology was done even, very early on. And then we started to investigate parameters, radiation dependence, doping. And one other important thing was RD50. I will come later back to RD50 again, the research, the R&D collaboration at CERN. And after understanding the parameters needed, there is a large-scale application, 15 by 15 pads in one array. Radiation was required, radiation tolerance was required, and a lot of very interesting investigation. Atlas and CMS decided to use it in the experiment, and you see then that at one point the large commercial manufacturer HBK came in to participate. And now we are in the fourth phase, namely combining tracking and timing in the same detector. We call it AC-LGAT. We want to combine spatial resolution of a few microns with a temporal resolution of about 10 to 20 picoseconds. And again, many different ideas which lead to 100 fill factor, the percentage of useful part of the detectors of 100%, sparse readout to have power, charge sharing, and so on. And again, the same institutions are still working on this, which is very good, including Hamamatsu decide now to start. And again, it will be RD50 and quite a few groups. Brookhaven is actually making some of these detectors, and KK is working with Hamamatsu to do this. And then there is a hope that there will be maps at one point, because it would make the cost and assembly material budget smaller. So again, two different contributing type of institutions, research institutions of a few hundred people maybe working there, and then a large commercial manufacturer. And there are more manufacturers on the verge of producing LGATs, which are applying for funding. But the progress was really driven by the small research institution working closely with this group of RD50. So just to set the scale, naturally, what's happening here is that the detectors are based on our silicon strip detectors, NNP, and what is being done is we just add one extra layer, which is a gain layer, highly with fairly high doping concentration. It increases the field in this region and produces multiplication, increases the signal. At the same time, the thickness is reduced, and the rise time is decreased, and so the LGATs have large and fast signals, which you need for timing. Now, this cartoon on the last page wasn't actually too simple, because the challenge is, or the devil is always in the details. You see now that there are a lot of things one has to worry about, like the ends of the N implant called JTE, and so on. I sent it here. So it's really it occupied us for several years to go through all of these things so that we would be ready for application. And a typical test run was about 15 wafers, and the participating institution would have maybe 1 or 2 runs every year. So it was a fair amount of work. And clearly some of these things like radiation damage is still being done right now. So here is sort of the scorecard of what we were able to do. We started out with 300 micron thick active thickness, and then within a year we went down to being able to go from about 200 picosecond down to 100 picosecond. Then we started to decrease the thickness of the detectors, and then in 2017 or so we established that 50 micron is a good thickness. We compared it to 80, also 80 micron, and now we are at 80 micron. And now we are at 20 microns, and we are at the 20 picosecond time resolution. And what was important is that we actually had a simulation program developed in Torino, which allowed us to predict some of this performance instead of just explaining it. So while doing this, we also had some, we looked at the rate capability. We did this at SSRL and then also at the APS. Here's a picture of a pulse train, which we took. The separation between these between the spikes is 2 nanoseconds, so you can see you can maintain 500 megahertz easily in the band structure. So again, something which we are looking at now, how much we can use these detectors in X-rays. The third phase was then that these LGADs, after fairly short time, really of being around, were adopted to solve the accidental background in the upgrade of the LHC, and both Atlas and CMS worked out and detectors in the forward direction. This cartoon here shows that for in that environment at the high luminosity LHC, you need to have the timing which is in the vertical direction to be able to help the position resolution in the horizontal direction to identify the real tracks, which is red in the environment of these blue tracks, which are shown here. What we did fairly early on, we have shared submissions between Atlas and CMS. We have, and another thing was that we talked with the manufacturers, which are shown here, Hamamatsu, CNM, FPK in Trento, and two companies in China, or institutes in China, to have the same layout, essentially same wafer layout, the same detectors and so on, same detector thickness, size, and so on, to allow this to happen. And we are now in a testing program and continuing testing program now on the production. And basically, this is a big job. Atlas needs about 11,000 6-inch wafers. So you have to have a large supplier, which will be supported by the institutes which I mentioned before. And most of the, if you're interested, there are TDRs which have been accepted, and they describe what we are planning to do. And just for you to see, we we are sharing wafers between Atlas and CMS. This is two different layouts. One of them is for large sensors, and the other one is for smaller sensors, which are being used to test all these parameters which I mentioned before, and they are shared between Atlas and CMS. So what with this in the bag, what are we going to do? We are now looking for the next phase, and that is really what we are talking about now. DOE has a basic research needs report. There's a slow mass process. There is the electron-ion collider, which needs sensors. And in the EU, there is an ECFA detector R&D roadmap process going on also. And basically, there is different research directions in the BRN, and one of them is picosecond timing, develop high spatial resolution pixel detectors, precise per pixel time resolution to resolve individual interactions in high collision environments. And the thrust one, namely an application, is lepton colliders requiring timing in the order of 10 picosecond, and then pixel pitch on the order of 10 microns. And we believe that this should be really be rephrased. It should be really that the spatial resolution should be 5 microns, because we believe that the next development will not have pixels and will have much larger distance between readout nodes. So here it is. So these are ACL guards, and again, to explain what's happening, you have you change again the layout of the L guard, get rid of all of these physical pixelation, which problems with p-stops, JTE, and stuff like this, and just replace it by a resistive N layer, add a dielectric on top, and then you read out the signals by AC pads, which you can adjust or locate in the way you need it. So much more simplified detector. There will be sparse readout. You can space these contacts here, AC pads, fairly far apart, and you can use a pulse sharing to get the position of the track. You simply simplify the design, and you have 100% fill factor. So this is now going on. This is while we speak, and just to show you what's happening. Here is a particle going into one of these ACL guards. The charge is collected on the N layer. It shows the N layer, and then pads here, and the charge is then spreads out in the N layer, is detected and allows the localization of the track. Normally, a sharing of a small signal among 4 channels would lead to inefficiency in low spatial precision. But here's a gain, which is below this N layer, makes this a very effective process. Here is a picture of an event. For pixels are sharing, the pulse is closest to pad 4, the signal is largest, then 3 and 2, I have to get rid. 3 and 2 have the same distance from the track, or from the laser in this case here. They have the same size, and then the one which is furthest away has a smaller signal. So between 4 and 6 paths will be read out and reconstructed in the location. The position is very good. This shows that the resolution, position resolution as a function of distance, and about 5% of the interpath distance is a resolution which is being reached now using lasers. So in the phase we are now, the summary is really that we can do very well. We can see a very good position resolution, about 5 micron, very good temporal resolution, 20 to 30 picoseconds, and 100% fill factor. We can make these detectors thin, or have to make them thin to actually get the resolution. One can vary the pixel size, and it helps to lower and making it large. It gives you 5 micron with sparse readout and lower power budget. And what we really have to do is work on the electronics, readout electronics. And we have to, the one thing we have to worry a little about is the high particle density application, which we have to find out how to do this. And in the future, there is an idea of combining AC LGATs with maps, and people in Brookhaven are working on this. So let me come now, this is one reminder about the electronics. We started out with boards and then went to ASICs. There is a very nice ASICs which are used for the high luminosity LHC. And Torini has worked on readout ASICs, and there is a very nice talk about the pedigree of timing ASICs by Federico Fausti at the IEEE. I want to come now to manufacturers, budgets, and so on and so on. Again, I mentioned this before, that there were really 2 types of manufacture. One, the institutes which are being supported by public funds, GNM, FBK, and Brookhaven, and Chinese companies. The funding sources shown here, all of them are non-commercial, and the exception is Hamamatsu. What is interesting is that quite a few of these detectors, these manufacturers actually have a history of working on SIPM, which are really very similar to the LGATs we are talking about. And so, but it also a connection through here is really, as I mentioned before, RD50 and RD50, which I will mention before. For LGATs, the new, I would think the new development are 8-inch wafers, which would naturally reduce the cost, and the Chinese institutes are working on this. In terms of AC LGAT, the FBK Trento has been very proactive in making a detailed investigation of the geometry and spatial and time resolution possible. Let me just talk a little about Hamamatsu. As I mentioned before, most of the technology advances have been driven by the small institutes, partially supported by public funds. The interaction has often been facilitated by RD50 membership. So HBK is the only big commercial company to work on LGARDs, and the cooperation is really based on the past, where we had very good relationship, starting with the SSC and continuing through GLASS, LHC, high luminosity LHC, which needed large production, which is actually attractive for a big company. And as I mentioned before, one way to get HBK to agree to work with us was that they are working on SIPM for medical application and so on. And so they had a lot of the background already in there. We contacted them at IEEE symposia and also Hiroshima workshops, and convinced them that there is a future market, and laid out a collaboration plan. Hamamatsu would deliver thin existing test structures, which also even SIPM, which they have, for us to test, and we tested them in the range of LGARD operations, namely low gain, about 10 to 20 or so. After receiving test structures, HBK made a LGARD production varying the thickness and also 4 different splits of doping concentration. These were then tested within RD50, especially radiation tested, and then the results were submitted to HCD and ETL Corporation for their TDR. We then started to have paid, funded prototypes where Atlas and CMS collaborate together and so get full-size LGARDs arrays produced by Hamamatsu. And we are very happy that now HBK has actually started to manufacture AC LGARDs also in collaboration with KK. Funding sources, again, prototype runs tend to be expensive, $50,000 to $100,000. And there are different sources for funding. One of them is regional funding in the EU. There is AIDA 2020, and then there is ERC, which gives fairly large contracts. There's national funding, Spain, the Spanish Ministry of Economy and Competitiveness is supporting CNM, Italy. INFN has a special Gruppo Cinque, a group which supports new instrumentation. There is a foreign minister, even there is a special contract between INFN and FBK. So there is a lot of support from the government. In Slovenia, there is a research agency. In the US, we have seen that the Detector R&D program, which is part of the DOE-based program, helped us in Santa Cruz a lot. But there are also funds which go through the lab directors. And then there are now construction funds for CMS, while Atlas will be not supported from construction funds in the United States, but only by R&D funds. And then there is a national funding with, for example, there is a cooperation program between the US and Japan. What I'd like to mention is the funding through collaborations, and that is RD50. We'll come back to it in a moment, which is located at CERN and 60 institutions, 400 members. And there are observers, many of them are manufacturers, and they actually contribute quite a lot of in-kind resources. And the funding comes out of the yearly contribution of 2,000 Swiss francs per institute. Again, a little more about RD50. I think it was clear that the system worked very well in this development of these LGARDs. Again, I mentioned already that it's a fairly large collaboration. The interaction is very open. There are 2 workshops per year. And a lot of communication in between. There is a common fund which collects the annual contribution to about 120,000 Swiss francs are collected every year, and then common projects are funded. A proposal for a common project needs a minimum number of participants and then a minimum number of 30% co-funding. So now we are looking at something interesting, because instead of having to pay, $100,000, you might only have to pay 30, and certainly it's possible for people to participate, or institutes to participate with small contribution. And there is another important part, namely in-kind contribution from the manufacturer. The project proposals are reviewed by a small internal group, and then are funded on the spot, so one can get going, one has a good idea, one gets funding, go ahead, and then one can go manufacture. And I think the selection process internal to RD50 guarantees, first of all, that there is a real collaborative spirit, but also that the real experts are reviewing the proposal. There is now a new idea. This comes partially out of the SNOMAS studies here, namely that we would like to have, we are thinking about a consortium for further LGARD development. The applications are obvious. It's the electron-ion collider, where there's interest in 4D track, TOF, and Roman pods in the forward direction. There are 2 organizers, Alessandro Tricoli and Reli. So it's lab and university is involved. There was a meeting now, and there were 27 attendees, which was good. Clearly, the need for electronics development was noted, and also it's clear that other applications like the CAPC would benefit from these developments. Okay, so here are a few points for the funding summary. How am I doing, Yin? In time?
On time, we're slightly over, but this is too good to interrupt. So
Okay.
what we're going to do is we're going to let you finish, and then we're going to take a short leg break for 5 minutes.
Okay.
Right.
I just have a few, right. Okay, so one of the things is which I try to show is that a lot of the funding is dispensed by funding agencies to manufacture in their own country, which is certainly true for overseas places. And so for us in the UNS, we really have to make sure that we strengthen and align the collaboration with these institutes in other countries. The CERN RD process really works quite well, but at one point projects separate into experiments, since the funding tends to be tied to experiments. I think the exception might be RD50, which has been now around for a very long time. And clearly the development of the LGARDs really benefited from it. The other point which was important is to actually share costs for the LGARD prototyping for the high luminosity LHC between Atlas and CMS. So that I think worked extremely well. For the electron-ion collider, we should consider a consortium approach, has been proposed, is being worked on. And one model would be to have a consortium be treated like an experiment, including an organizational chart, planning, and funding. And just to bring an example for this type of operation is that is the fact that the German Helmholtz-Gesellschaft, out of their innovation pool program, has just awarded a fairly large amount of funding to an R&D collaboration, Tangerine, to develop maps, IC LGAPs, and also AI. So here is my summary. So we worked on these LGAPs for 7 years. They have reached a status of maturity that they are going to be built into the upgrades of the high luminosity LHC detectors, where the temperature resolution will be used. The next step is the ACL guard, where the good time resolution will be maintained, but where additionally the position resolution will be added. And one of the attractions is naturally the simplification of design and the lowering of the power budget. And there are some consideration also of monolithic AC LGADs, which hopefully will come along. One of the items which really have to be done is more work on the readout ASICs. And one point I try to show is that this fast development of LGADs was really only possible by a strong collaboration between institutes, manufacturers, a commercial company, and funding agencies. And there is now movement to organize a consortium for future development of LGADs to pool the know-how and the pay-how. And one example would be this experiment, this R&D Tangerine, which is paid for by the German Helmholtz-Gesellschaft. That's it.
So thank you very much, Hartmut. That was a wonderful talk. So first, I'd like to thank Stephen Toki and Hartmut again for really informative, germane talks for this session. We're now going to take a 5-minute stretch your legs break and come back at, therefore, 9:47 when we restart with the final 2 talks of the morning session. Thank you very much. See you all in 5 minutes.
We're gonna leave the connection on, and then we need to disconnect and reconnect or anything like that.
Maurice, did you say we need to disconnect?
There is no need to disconnect.
No need to disconnect.
No
Okay.
need.
So maybe I should go ahead and share my screen so we're ready to go.
Yeah, that sounds good.
So you see that okay?
Yep.
Okay, good.
Somebody's typing and it really is coming across. Can they mute perhaps?
To connect your business to what matters most, whether it's customers, coworkers, or the cloud. We're with your business every step of the way, delivering internet speeds up to 1 gig, advanced phone solutions like hosted voice that can unify communication, and one-on-one attention to help you succeed. Connect with our business experts to explore your possibilities. And learn how you can save up to 20% today.
Hello, everybody. So we're ready to restart the session. I hope you all managed to stretch your legs. And so the next speaker will be Ken Markin from the Office of High Energy Physics at the Office of Science of the Department of Energy. And he'll be telling us about the DOE High Energy Physics, SBIR and STTR programs. So over to you, Ken.
Okay, hello everyone, wherever you may be. Here's my outline. I'm going to give you an overview of the federal SBIR STTR program and then the DOE one. And for these, I will use slides that are prepared and provided to me by Manny Oliver, who heads the DOE SBIR effort. And then I'll discuss a little bit about the elements from my view of a successful SBIR within the HEP context, and then some examples of some success stories. So these are Manny's slides. The SBIR STTR program is a congressionally mandated program, and it applies to all federal government offices that have a extramural R&D budget that goes outside greater than certain thresholds, which we'll show in a minute. And Congress has stipulated that these organizations must take off the top a certain percentage of their extramural R&D funds. So in the US, this amounts to approximately 3.6 billion per year, which is directed from the extramural research budgets to small businesses. The overall goals set by Congress in the Small Business Innovation Research Program, which was established in '82, is to stimulate technical innovation, use small businesses to meet federal R&D needs, foster and encourage participation by women and socially and economically disadvantaged persons in the technological innovation area, and to increase private sector commercialization of innovations that are derived from federal R&D. The STTR came about 10 years later, and its aim is to stimulate and foster scientific and technological innovation through cooperation between research institutions and the small businesses, and to foster technology transfer between small businesses and research institutions. So the percentage levels that are diverted to these programs are stipulated by Congress. They have grown over the years. Today, it's a total of 3.65%, 3.2 of which goes to the SBIR, and 0.45% goes to the STTR. The STTR is only for agencies whose extramural R&D exceeds $1 billion a year. SBIR applies to all federal agencies that fund extramural research greater than 100 million a year. So I'm not going to go through this slide in detail, but it gives you a flavor of how this program applies to different agencies. You can see about half the funding comes from the Department of Defense. The next biggest one is DHS, and DOE ranks third with about a $280 million investment a year in SBIR STTR. The program works in 3 phases. Phase 1 is feasibility or proof of concept. The award amount, there are maximums set. Actually, this program is administered by the Small Business Administration in the US, and they set these amounts. They vary a bit by agency, but you can see it's between 170 and 250,000 for phase 1, and the period of performance can be 6 to 12 months. Phase 2 is to continue on to prototyping or process development, depending on what the award is for. The awards vary between 1.1 and 1.7 million. The project duration is 2 years, and there are provisions for follow-on sequential phase 2 awards in various flavors. And then we talk about a phase 3 commercialization, but there are no SBIR funds that go to this. We like to track what happens with these projects after the SBIR funding has stopped. So commercialization phase, there are no dollar or time limits clearly, but no SBIR funds. There's a special class of SBIRs called technology transfer opportunities. These are ideas, or this is inventions that have been made by the US national labs, and they are offered to small businesses for commercialization. Awardees receive an SBIR STTR grant and an option to license the technology from the laboratory. Funding limits may be higher for the TTO awards than they are for the standard awards. And we have an example in high energy physics of INCOM, who won a fiscal year 13 phase 1 TTO award for the LAPPD technology from Argonne. So moving on to the Department of Energy in particular, we are a mission-driven agency. Here are our high-level goals. 1, to catalyze timely, material, and efficient transformation of the nation's energy systems and secure US leadership in energy technologies. And these goals are mapped onto the SBIR and STTR program primarily in what we call the applied energy offices. The second goal, maintain a vibrant US effort in science and engineering as a cornerstone of our economic prosperity with clear leadership in strategic areas. And this maps onto SBIR in the Office of Science program offices, including high energy physics and nuclear physics, who you will hear about here. The third goal, to enhance nuclear security through defense, non-proliferation, and environmental efforts, maps onto portions of what we call the NNSA, the National Security Agency. So moving on to high energy physics. The high energy physics mission, as most of you are familiar with, understand how our universe works at its most fundamental level. We do this by discovering elementary constituents of matter and energy, exploring the basic nature of space and time itself, and probing the interactions between them. To enable these discoveries, HEP supports theoretical and experimental research in both elementary particle physics, but also in fundamental accelerator science and technology. And this is the particular thrust and particular mission element that our SBIR and STTR programs address. So to put it in the context of the office, here is our org chart today. We're two main divisions. One is the Research and Technology Division. The other is Facilities, which maintains our facility operations and also projects. But the SBIR resides in the Research Technology line, which includes General Accelerator R&D, Detector R&D under Helmet, Computational HEP and QIS, and SBIR STTR, which relates to all of these and provides opportunities to small business down this line. So for the most recent year, FY20, these were our topics. Actually, our 21 topics reflect them, but they haven't changed a lot. So the main topics: advanced concepts, advanced accelerator concepts. Radio frequency accelerator technology includes both normal conducting and superconducting. Laser technology R&D for accelerators, superconducting magnet technology for accelerators, high energy physics electronics, detectors and instrumentation, and more recently we have added quantum information science supporting technologies. And I don't do all this alone, although I have portfolio oversight for this whole range, but we have technical topic managers who are better experts in each of these areas than I am. And you can see here the people that have the TTM responsibilities for these various topics. To give you a sense of numbers of awards and win rates, these are the last 5 years statistics. The phase 1 win rate tends to run 20 to 25%. It was up slightly in 2020 because we had some money that came back to us in the form of prior year awards that were canceled or let go. Phase 2, the typical success rate is around 40%. You can see last year we made about 16 phase 2 awards. And then the sequential phase 2s, really difficult to statistically give a percentage. It varies considerably year by year, but last year it was about a 25% success rate for the sequential phase 2s. The maximum award amounts have recently gone up. Prior to FY20, they were 150K for a phase 1 and 1 million for a phase 2. In 20 and 21, they went up to 200K and 1.1 million. And in FY20, the HEP funding for SBIR STTR was a little over 25.5 million. The average over the last 5 years has been about 24 million. So how do we come up with our topics? There's an annual call from the SBIR STTR program office. We at a high level, the HEP associate director sends a request for our topics and topic language to our key laboratory partners. Prior year topics are provided as a reference. Updates to existing topic language are requested. We also ask for proposals for new topic ideas that relate to upcoming projects and mission. And specific specifications or performance targets are encouraged in the topic language that we request. So from the language that we receive, and we always do receive a substantial amount of input from our laboratory partners, topic selections are based on, number one, the strategic importance to the HEP mission, the commercial potential beyond high energy physics. We look for a time horizon that's generally commensurate with a typical SBIR STTR funding cycle of 3 to 5 years, and coordination with existing and prior topics in our sister offices who also fund accelerator and detector technology. So moving on, elements of a successful proposal to HEP. This almost goes without saying, but there must be technical innovation. These are not just for commercial development, but we need a new idea that advances both our mission and commercial potential. So the commercial potential for a proposal must be clear with a sensible commercialization plan that addresses the market opportunity. Similarly, the strategic importance to HEP must be clear with a well-articulated impact on a specific mission need. I will note that our mission needs include general technology advances, which includes performance improvements and cost reduction. It can be specific accelerator improvement projects that are underway or anticipated, capital equipment activities, midterm upgrade plans to existing experiments or facilities, and also midterm directed R&D. So all of those things qualify as being strategically important to us. And again, typically the time horizon should be in the 3 to 5 year time, which is a 1 to 2 phase 2 award cycle. Although we have many examples of truly innovative ideas which branch and extend and run into multiple phase 2s. And another element, projected return on investment from the technology should be sufficient to justify the agency investment, which for phase 2 is $1 million a piece. So we're looking for anticipated returns that may be 10 times that. Additional elements for success: close collaboration with a national laboratory and or a DOE funded university group is quite often a characteristic of a successful SBIR project. Supporting letters from labs or university scientists working in the specific technology area provide strong evidence to our reviewers of relevance and tend to result in better outcomes. And expressions of interest from potential customers help demonstrate the commercial potential. So just a few comments I will make on metrics over the last decade or so. Prior to 2011, we had many instances of Office of Science SBIR STTR awards being used primarily as industrial R&D, resulting in interesting and new technology, which was often very helpful, but no product in particular. And this was sort of a way of life up to the 2011 congressional reauthorization. And in that language, Congress put an increased emphasis on commercialization and required agencies to develop commercialization metrics. So some of the resulting changes in the DOE program include a multi-level review of topics, including our legal counsel, looking for commercial potential and making sure it was there. Our general counsel office will flag topics that we send that appear to have a federal program as a primary customer. So we need relevance to mission, but we need customers, potential customers outside of the federal enterprise. So starting in 2012, a rudimentary commercialization plan is required for a phase 1 proposal, which it was not before. And the DOE SBIR office has now put in place metrics for commercialization, including revenue forecast and commercialization history. So I would say, and from personal observation, many companies have adapted well to these changes, resulting in much stronger commercialization plans and commercial success. I didn't write it down here, but conversely, there are some companies that have not, that had long-running SBIR efforts with high energy physics, which no longer they do because they have not adapted well to the greater emphasis on commercialization. Part of the statute is that the program must be reviewed periodically by national academies. So the most recent National Academy's review of the DOE SBIR program was in 2020. This one took a different turn from some prior ones and did not look closely at commercialization. The previous 2016 study did, and they surveyed many of our SBIR businesses and came back with these commercialization results. About half of respondents reported some sales. A further 23% reported anticipating future sales based upon their SBIR project. About 78% of respondents reported receiving additional investment funding in the technology that was related to their SBIR projects surveyed. 71% reported the project probably or definitely would not have proceeded without SBIR STTR funding. 45% of companies indicated the company was founded entirely or in part because of the SBIR program. And about 60% of respondents indicated that the DOE SBIR STTR program had a highly positive or transformative effect on their company. So looking forward, the DOE SBIR office has been trying to further refine and develop their commercialization metrics. There is a commercialization survey that has been developed, which relies on self-reporting from our companies. And they are working today on incorporating that into our portfolio analysis and management system. We expect to see that in the near future, in which case we expect to get much better information and statistics back from our companies Today, I do not know by program office, for example, numbers and statistics for commercial success, but we expect to have that in the coming years. Today, our phase 3 success stories provide useful information to other firms on how to succeed, and it also helps us formulate strategies to foster success in somewhat different situations. So analysis of the successes sort of fall into 3 different kinds of firms: those that receive only 1 or a few awards from DOE, and these are typically firms addressing larger commercial markets who can rapidly transition to private investment. The second category is firms that receive many phase 1 or 2 awards from DOE, and these are typically deep tech opportunities that may take many awards and many years to fully develop the technology. And many of the Office of Science programs fall into this category. Manny Oliver provided me with an example that would be KM Labs, and I'll show you that story in a moment. I would say that another one is INCOM and LAPPD. So in this group, implementing second or third phase 2 awards has been very important for success. The third instance is firms that receive many phase 1 or 2 awards across multiple agencies. And these companies typically work on platform technologies that are useful to more than one agency and other agencies. So the last part of my story is showing some particular examples of phase 3 success. I have at the top of the list INCOM, and I'm not going to go into this in detail. There was a separate part of this session on Tuesday, which discussed LAPPD in detail. I think many of you know what this technology is about. It has been supported through SBIR from high energy physics, nuclear physics, and BES. There have been 5 DOE phase 2s and 3 phase 2A awards since 2014. And I think many of you know prototype fabrication since 2017, pilot production since 2020. So the takeaway message here is these fast, high resolution, high sensitivity, and low cost photodetectors, manufacturers' large tiles, are expected to enable better science detectors and new commercial applications. So my read of the success elements here includes a high priority mission need across HEP, NP, and BES, close cooperation with a broad national detector collaboration, and multiple phase 2 awards over an extended period have all contributed to the success enjoyed so far. KM Labs is a spin-off business from GILA, a lab at the University of Colorado Boulder and NIST. The technology is a tabletop femtosecond pulsed X-ray laser for both imaging and time-resolved spectroscopy. There are broad applications in the semiconductor industry, in bioimaging, and in neuroscience. So the commercialization timeline in this case, SBIR support started in 2002 with a DoD grant. There have been 6 DOE phase 2 awards since 2007, resulting to date in about 14 million in product sales and about 13 million in 2 rounds of investment. So what I see as success elements here, again, a high priority mission need across multiple Office of Science agencies as well as within DoD, strong market pull in multiple areas, multiple phase 2 awards over an extended period of time, and in addition, follow-on venture capital investment. This is one in my area, high temperature superconductors. This is a high temperature superconductor magnet cable made out of Rebco tapes. So one of the drawbacks technically to the second generation HTS conductors, as we call them, is they are manufactured with thin film technology in the form of tapes. Advanced conductor technologies has taken these thin tapes and found a way to wind them not only into magnet cables, but also much smaller diameter things in the same technical way, which we're calling wires. Their advantage is they can be bent around much smaller diameters. So the impact of this technology, it's already going into our HTS magnet development program, and we expect it to enable superconducting magnets producing fields of 20 Tesla and beyond. It's also being developed for demountable toroidal field coils for the next generation fusion reactors. And it's also of great interest for future research in medical particle accelerator magnets. They have received funding from both fusion energy sciences and high energy physics. And 5 years after the end of their first SBIR award, they have achieved a sales revenue over 1.5 million, including several purchases by Lawrence Berkeley Lab to build the first quark, which this cable is called, quark-based accelerator magnets. Successful elements in this endeavor have been, again, a high priority mission need for both high energy physics and fusion energy sciences. They had a strong early interest and early purchases from CERN, and they have had a very close continuing cooperation, both with a wire manufacturer who provides the tapes, several university groups in our superconducting magnet program, and the US Magnet Development Program. And again, multiple phase 2 awards have contributed to their success. We're doing okay on time here. Yeah, it looks like we got a little bit. TechX Corporation is a software development program. The success is for their vSim platform, which is a flexible multi-platform, multi-physics simulation software tool. It can run computationally intensive electromagnetic, electrostatic, in the presence of complex dielectric, magnetic, and metallic shapes. So there's been broad interest in this across multiple federal agencies. They've received funding from most of the Office of Science program offices, and they're in the DoD metric of grading these things at the 70th percentile among all SBIR awardees in the Department of Defense commercialization ranking. They have reached over 30 million in product sales and research services. Success elements: high priority mission need across multiple federal agencies, broad market pull across a range of technical arenas, close cooperation with university and lab groups, and multiple phase 2 awards. So those are the ones most relevant to HEP. I've given some other examples here, which I got from Manny Oliver and from other parts of the program. So Telecent has developed fiber optic interconnects for large data center connections and optical switching. They got 3 DOE phase 2 awards and a phase 2B since 2010. And they've had 5 million in product sales, which is rapidly growing. And in addition to that, private investment. I meant to ask Michelle how to say the name of this company. I'm not familiar with them. I think it's Xia, but they have been funded by nuclear physics, BES, and also some SBIR efforts under the NNSA. So they make a compact digital pulse processor for X-ray applications, a complete low-power digital spectroscopy system on a credit card-sized PC board. They have sold in excess of 20 million in instruments for synchrotrons and multi-million-dollar revenues per year from sales of its product lines. And Scutech, again, has received nuclear physics SBIR funding. They have multi-channel digitizers addressing the need for cost-effective, high-density data acquisition for the newest generation of experiments in both nuclear and high-energy physics. And they're still involved in a phase 2B DOE SBIR award, but they have growing sales, 78,000 in non-SBIR funding, 71,000 in sale revenues, and a large pending purchase order. So that's what I had to say. I will stop at this point.
So thank you very much, Ken. That was a terrific overview of the entire program. We have about 5 minutes for a few questions before moving to Michelle's talk. So if you could indicate your interest in asking a question by raising your hand, and Helmut was very quick off the starting block. So Helmut, please.
Right, so I wanted to make a comment about the amount of funding and time it takes from first idea to commercial product. And both of them are much larger than maybe meets the eye. And taking LAPPD as an example, the total investment in that, starting in 2009 with a $5 million allotment from ARA funds, comes to something approaching $30 million by now, being a mix of research funding to labs and universities, LDRD funding, technology transfer funding, and SBIR funding, which actually spreads across HEP and BES. So this is a rather significant amount of money and a rather long time frame really to get from the first idea to the product. And that is something one needs to keep in mind.
A very good example of what Manny is calling a deep technology company that requires extended periods in funding. So no, it's a very, very valid comment, Helmut. Of course, we have examples of success on shorter time frames, but the LAPPD is an interesting example and very important to keep in mind the sustained investment that is required for success in some of these areas.
Do you think that there's a deep understanding of that need for sustained success, or are there often discussions about, well, how long does this really need to be funded for? I mean, how enlightened is the decision-making process? It sounds very enlightened in the examples you gave.
It's a regular point of discussion, and I'm not going to talk about it, but I will say those of you who follow Department of Energy organizational structure, in FY21, there was a new office added. It's in the Office of Science Management chain, and it's called the Office of Accelerator R&D and Production. And my understanding of this office, which we will hear more about in the coming months, is to address exactly this problem. So we have many examples where the US started down a path of sustained investment in a particular technology and did not follow through. And the best one that I can think of is superconducting RF technology. So there's a large number of SRF cavities and cryomodules being made for the LCOS2 upgrade, but much of the technology and much of the manufacturing is being done outside the US. So it's recognized that we need to find mechanisms to pursue longer term investment in technology such as this.
Thank you for that answer. That was very clear. Toki has a question, and then we're going to move to Michelle for the next talk.
Yeah, as I talked, I enjoy working with a lot of companies through SBIR, and that led to some successes. But whenever I apply, I always have a question about what is the difference between SBIR and STTR? Like how should I pick to apply the one to the other? Is there like a simplified version for the person like me to kind of use to understand that?
So yeah, I mean, that was one of Manny's slides, which I did not elect to keep in the interest of time. But the basic difference is STTR requires significant participation by a research institution. So in your case, Berkeley could stand to get significantly more funding from an STTR than from an SBIR. So the STTR can allow up to 50% of the funding to go to the research institution, whereas for an SBIR, it's only 30%. Now, there's some subtleties there and some differences in phase 1 and phase 2, so you need to look carefully at the FOA to understand the details. But basically, an STTR is intended to foster technology transfer from a laboratory or another research institution to a small business, and they are allowed to supply more of the funding to the research institution.
Thank you.
Thank you. Thank you very much.
Another factor in the decision, of course, is the amount of funding for the STTR is significantly less. So it's about the SBIR funding amount available is about 7 times more than an STTR. And I will say that if you're very careful about how you formulate budgets, you can actually submit a proposal to both SBIR and STTR. And many times, I haven't done the statistics, but my instinct tells me that the success rate for phase 1 proposals submitted to both is higher than it is for either of the individual ones, because it gives the program manager some flexibility. And sometimes we don't have a good enough STTR to award all of them that we can. Sometimes it's vice versa. And if we have the flexibility to make the award one way or the other, it makes it easier for us to make an award decision. So a little bit of inside information there.
That's very valuable to everybody joining here today, I think. Thank you for that. And again, thank you for your talk, Ken. We're now going to keep to the theme of SBIRs, but looking at one area in particular now and focus on nuclear physics. And we have Michelle Shin joining us today to tell us all about that. So Michelle, if you'd like to share your slides.
Okay, I had to move to my bedroom at my parents' house. This is my old bedroom from forever. So let me go ahead and share. Let's see here. Why am I being, oh, here we go, the big green button. And normally I can just go right to it, but I'm suddenly being slow. My apologies. It's buried. There we go. And let me go ahead and go full screen. Okay, do you all see, Ian et al., do you all see my slides?
We see them very clearly.
Wonderful, excellent. So Ken gave, Ken and I have been talking and we've been trying to coordinate on all of this. So I really do appreciate him spending all that time to introduce you all to the DOE SBIR program. And also I'd like to thank Ian and Gabriela et al. For giving me the opportunity to speak to you all. I see a lot of familiar faces. And I also see some new folks. And so this is really exciting to me as I see particle physics writ large as very collaborative and with a lot of overlap. So a teensy bit of quick background. I have 18 slides. As program manager for industrial concepts, it was a new position created in the Office of Nuclear Physics in 2016, and I was a successful candidate. And I've been trying to make a number of changes supported by leadership and the office, actually. And I are going to see some of the effects and some of the things that I've been doing to make this a more effective program, both for our communities and also for the businesses, which we're trying to. This is a federal industrial, and again the community aspects. So without further ado, very quick outline. I'm going to talk about the mission and the facilities very briefly. And then how the community, primarily nuclear physics, of course, influences the topic development and selection of proposals. And when we do that, writ large, it's advanced technologies that are unique, more or less, to nuclear physics, and also develop software tools and hardware to advance NP initiatives in advanced technology. We've got a lot of initiatives, some unique to increase commercialization. I'm going to actually speak about dollars and cents. Well, actually just dollars, in this case, mega dollars, and then some observations and conclusions. So I don't think this is too new to most folks, and I'm actually going to move this little teeny bit of Zoom stuff over to one side. Nuclear physics is to discover, explore, and understand all forms of nuclear matter. So our challenges are the existence and properties under extreme conditions, including those that existed not at the absolute beginning of the universe, but give us some give us some femtoseconds to nanoseconds. The exotic and excited bound states of quarks and gluons, including new tests of the standard model. In some of that case, I'm going to also refer to the last bullet on these tests of standard model. We look at try to explore the ultimate existence of bound systems of protons and neutrons, the nuclear processes that power the stars, the supernovae, neutron star mergers, and the synthesis of the elements that results, and the nature and fundamental properties of neutrons and the neutrino, and their role in the evolution of that early universe. So this is all being done. We use our scientific user facilities, the Relativistic Heavy Ion Collider here across the bottom at Brookhaven National Lab, the Continuous Electron Beam Accelerator Facility at Jefferson Laboratories, and at Atlas at Argonne, primarily a low energy or a nuclear structure, nuclear astrophysics lab. And then one more, well, I guess I have to get to this slide. There, oops, FRIB. FRIB, which is under construction and really going beautifully. Really the last part of FRIB is actually the turning around, if you know about how the NSCL, the National Superconducting Cyclotron Lab, works at MSU. There's a configuration for all the experimental hall called the A1900, and they basically have to rotate that 180 degrees. So it's very close to being done. Again, we have these 4 user facilities. And it's rather remarkable that an accelerator at FRIB is if you could unfold it, actually really runs down the length of one long line of CBAF. It's quite remarkable. It's folded in on itself, sort of like a paperclip. So how does the mission of the nuclear physics translate into programs? So our major program areas are heavy ion nuclear physics, that's at RIC, also some at the LHC, medium energy physics, that's primarily at Jefferson Laboratories, nuclear structure, nuclear astrophysics at Atlas, and it will also be co-done at also at FRIB, and then fundamental symmetries. And that's being explored both internationally and with demonstrators that are deep underground in most cases in the United States and Canada, and then nuclear theory. I might point out that accelerator science and technology is a major component that facilitates all of the subprograms. Theory can't work in complete absence, right, of experiments. So Ken reminded me in his talk that I really need to point out that I don't do this all alone. I put up this is a bit of an eye chart, but I'll just say that I work also with subject matter experts. My main area is in accelerators, although I've really become a jack of all trades since coming here in 2013. In software, we have Gulshan Ray, who a lot of you know. In electronics, Manusha Fakande. And then in instrumentation is Elizabeth Bartosh. We did have an isotope for a long time topic, but in 2020, as part of the reorganization Ken mentioned, it became its own office and it will no longer participate in the SBI or STTR program. The topics in FY21 that we're now doing are in the 4 areas entitled software and data management, electronics design and fabrication, accelerator technology, instrumentation, detection systems, and techniques. Every year there is subtopic revision, primarily based on community input. And for my international colleagues that maybe don't think about fiscal years in the US terms, FY is fiscal year. And then for this, we are now in FY21, that runs from October 1st to this coming next September next year. So there's a few things that I've tried to do that are maybe a little bit unique. Clearly, we try to really tie the NP mission and strategic priorities to the community and the facilities it uses. So this grew out of my close reading of the 2016 National Academy of Sciences review of DOE, SBI, or SDTR. One of the things where two recommendations. DOE should seek to develop programs linking laboratories' procurement actions with relevant SBIR, STTR projects. And DOE should examine from a strategic perspective how the relationship of the program works today with the national labs. Because what we see a lot of times is that a national lab will like to collaborate with a small business while they have the award. But once the award ends, if it's not at a point where they can now really use it, then they pretty much drop it and move on. And it's just a fact of life that everybody's program is funding limited, right? So one way to make the adoption by a lab of a product from a grant that's finished is to require, and I mean require, that a prototype or method be ready for testing by the grant's conclusion. So that means that there'll be hardware, software that can be rapidly purchased, right? And deployed to fulfill the community needs, which should be leading to higher rates of commercialization. And I only have, in my really hard working attempt to get this data, I only have 2 FYs, 18 and 19, but there is an increase. I'm encouraged. So in doing that, subtopic requests must be right-sized and timed. So what we do is we match the facility accelerator improvement plans and capital equipment activities and any midterm upgrade plans to the 3-year SBIR, STTR funding cycle. And we do the same for universities and other collaborations working on detectors. I coordinate with the other offices very closely with HEP, very closely with BES to not duplicate efforts unless a particular technology is synergistic. And an example is lowering cavity, SRF cavity fabrication that would benefit from that other investment. A second, and Ken alluded to this, is the LAPPD development. I might say, I can't say that Helmut and I are quite joined at the hip, but Helmut and I we're very careful to coordinate across and to share any communications that we get from the field, from the company, with each other. Although the company is very good about doing that and has been from the beginning. If there's any little thing, I like to share it, and I share it in the office. And projects must be of sufficient value to the NP community to justify the investment in the first place. So a quick look, what is that investment? What's that investment look like? How much money are we talking about? Well, here's a shot across 11 years, 08 to 18. The total value of NP grants was $81 million US. And 118 companies were funded, some multiple times during this time span. So, I mean, that's a lot of money. 81 million is a major item of equipment in many cases. I mean, a large instrumentation project. And in a given typical year, sort of from 19 through probably even this year, about 20 million US are awarded. And this is across all phases, phase 1, phase 2, and the sequentials. So that's a lot of money. And so we try very hard to work really emphasizing what I call our brand. So our subtopics really reflect this strategy. Use the funding of small businesses to maintain leadership in technology areas where we have unique needs. And we do have obviously cross needs and synergistic needs with, say, with HEP in particular. So SRF's accelerators and related technologies like cryogenics, that's synergistic. Polarized sources, HEP doesn't really need polarized sources in fact, I think we're really very unique there. And we're talking light ions in particular, although Rick will polarize just about anything. But since the degree of polarization kind of goes as A, you get less and less polarization as you get heavier and heavier atomic masses. CWRF sources, that used to be really our niche, but again, HEP and across the world, they're needing more of that. We need high current ion sources. Again, if you're going to be doing collisions and you're going to be doing something where it's a very weak interaction, the more current you've got, the better off you are. Detectors with a strong emphasis on particle ID, and microelectronics for extreme environments, such as high radiation from a range of heavy ions, and also below 2 Kelvin cryogenics for our fundamental symmetries. We're also interested in applicable any R&D that advances the recently published DOE initiatives in AI and machine learning, large-scale instrumentation, microelectronics, and quantum information science or instrument science. And that's all. I have a link that you'll be getting eventually when this gets uploaded. Again, it's something that I feel strongly about, is that the real key to commercialization is to build the relationships between the community and the small businesses. So what we do is we foster those partnerships. And the conundrum really is, how is a federal agency publicize a company's product to a wider community without creating or seeming to create an unfair advantage? Because you see, we do awards, we don't do contracts. So at the end of the day, the company produces a final report, which now is embargoed. If the community doesn't know about it, except through a glancing chance at a meeting, how do I make that work? So what I do is I use the required public announcement of awards put out by the SBIR office, and you can find 3 years of awards on their awards page, and I make that public to all the reviewers that we do in any given year, leadership at facilities and universities, and knowing what companies are receiving awards. That helps focus that. I also add all DOE press releases to the news section on our landing page, and all of this I keep disseminating to our community. It's thousands. It's a big group email. Let's see here. There we go. Other activities since FY18, we co-fund awards with other SBIR, other Office of Sciences offices. And in 20, we contributed to Oscar, BES, and HEP awards. The research division program managers now ask all their PIs to look at SBIR, STTR awards for possible collaboration or a source of hardware software. And these research PIs also know about all the awards. So if something that they know in the back of their mind, or they know, hey, this could work, this could be a source of collaboration, and it doesn't come up, they bring it up. Also, since 2017, I offer communities an opportunity to have a kickoff meeting about 1 month after they receive funding. And the idea is that during the meeting, I have community members, either I discuss who they should contact, or I actually have them on the Zoom call or the telecon, so that they can get to know each other. And that makes sure there's compatibility from the outset for meeting the needs. Ken spent a little bit of time on a new sequential award called Phase 2C that's been rolled out over the last 2 FYs. It mandates that all agencies that do SBIR issue a third Phase 2 at $1 million. Applicants must have received an initial Phase 2 and a second Phase 2 sequential, either an A or a B. Applicants are required to have one-to-one matching funds. And the idea is that this again helps them move a product, an SBIR award, into the market. Last year, we were the first office in DOE to award a Phase 2C to a company known as AlphaCore, and it was an electronics one. So we're very proud of that. Kind of moving down towards the end, other things, talking about my commercialization work. So DOE SBIR has to collect Phase 3, which is other, as Ken pointed out, other or non-federal, mainly other federal funding, but it's really anything that's not SBIR. And they only look at the US national labs. So in writing PIs, what I've done is I've expanded the request to include sales to other US and foreign research institutions. I've collected responses beginning from again, 2018. And so not everyone responded, but most do. So the numbers represent a lower bound, and I do this annually. So in FY19, Phase 3 and other worldwide sales was 20.5 million. Now that was dominated by a single 15 million accelerator award. So if you take the other 5.5 million that was self-reported, that represents an increase of 40% over FY18, primarily due to increased sales to other research institutions rather than the federal labs. The federal labs was pretty constant at about 2.5. Accelerator sales primarily are in sources, magnet components, and diagnostics, not at SC cavities, but in sources, magnet components, and diagnostics accounted for about 25% of the total. The majority was instrumentation, you'll be glad to know, detectors and electronics. And if you look and you pair up the award, the SBIR award, against the year that you're asking about, the majority of the sales of the hardware is based on awards made over 5 years ago. So that underscores that fact that it takes time for these phase 2 prototypes to become products. And it underscores what Helmut was talking about, as well as my friend Ken. So a quick SBIR success story. This is PhD's company located in Knoxville, Tennessee, and they make high purity germanium. And a number of SBIR awards has really created a very novel gamma ray imaging detector. So our initial awards did the crystal growth. Actually, I've got a pointer, right? Supposedly. The high purity crystal growth, fabrication, and you can see the segmentation that ties in, and then to an integrated detector assembly right here. When I got here in 18, they claimed that it was portable, but it was like 55 pounds. Now they're actually down to the smallest one, called a fulcrum, is now 7 pounds. So, you know, like 3-point-something kilos. These imaging detectors are used in basic nuclear physics research, as well as nuclear safeguards and security. This unique characteristic has resulted in sizable sales volume of their radioisotope imagers to national labs, as well as overseas. And like I said, the fulcrum is actually the lightest compact detector with a very analysis and readout right on board in the world. And this is all courtesy of a slide and information from Ethan Hull, PhDs. Here's a quick example. This is actually a separation going on in a hot cell, looking at the position of actinium-225 and radium-225 in a column. And you can see the glowing. So you've got an overall camera, and then you've got an area of interest. And here you're seeing a whole plot of all the different gamma ray lines. So there's a 40 keV 225 radium, but then at 99.8 keV is actinium. And you can actually home in on that and change the color codes so you know where things are. It's pretty cool. It's all on board. So in conclusions, I think I'm at the conclusions. We use the congressionally mandated program to ensure R&D that benefits the community, as well as greater particle physics folks, to build and sustain a US-based commercial infrastructure that serves society in areas beyond nuclear science. We have a set aside over 5 years, and it's equivalent to that for a major item of equipment like a detector. And again, with input from my program managers, the community, we use those funds for R&D that advances our core technologies, as well as new initiatives. We also have a very unique program. It's called the Annual Exchange Meeting. And we foster that connection where we have our program managers from the other offices, and from other federal agencies like NSF and NIH. And that gives opportunities from these other companies to meet these programs, meet these businesses. And I have actually seen new starts occur with other agencies because of this, this participation. I've also seen, and I'm really proud of this, is you also see this fostering of work between small businesses, because one company says, hey, that company's doing just what I need. Why should I spend the time designing it? So there's a lot of commercialization success stories, and Ken very thoughtfully gave a number of them, and I'll be providing you all a link. And that's it. Thank you.
Michelle, thank you very much. That was really a very, very interesting talk as well, and very well matched to what Ken had to say. You really worked very well as a team.
We really do. I miss Ken. I really do. I miss Ken. I miss my friends over in HEP. But, I can't go down to see Helmut. Anyway. Thank you.
Yeah,
it really bespeaks the fact that we're all a team.
Absolutely, and it's wonderful to see. Really wonderful. It's great for the community, and it's great for the office as well.
Thank you.
We have time for just a couple of questions before we move to the break. And the break, at the end of the break, we'll rejoin for the panel, which will include the 5 speakers that we've heard so far, plus a couple of extra people. So Just a couple of questions before we move to taking the break. Who has a question? Please raise your hand.
I'm going to stop sharing for a moment so I can see this chat.
That's right. You can see the chat too. I'm trying to see if there's any questions here. Well, maybe everybody's decided to wait till the
hungry.
panel, which
Right.
might be
Well,
the
that
case.
works. That
It
works.
may- yeah. Let's see. So if there are no, I mean, I could certainly ask a question now, but I think I would wait till the panel actually.
Okay.
Yeah.
So just for everyone's, I'm going to disconnect and close the meeting, and you'll have to reconnect. And
Okay.
so the break will be 20 minutes. So we'll start at 11:05.
All right.
Thanks. So thanks again to all the speakers today. Goodbye, everyone, and see you all in 20 minutes.
Cheers.
Bye.
Bye.